Radical cyclization reactions are among the most powerful and versatile methods for construction of mono and polycyclic systems. The advantage of these reactions offered to synthetic organic chemists include high functional group tolerance and mild reaction conditions, combined with high level of regio and stereochemistry. Furthermore, the recent progress in radical chemistry has led to the development of broad range of very useful practical methods to conduct radical cyclization reaction. In general, radical cyclization reaction comprises three basic steps, which are selective radical generation, radical cyclization, and conversion of cyclized radical to the product. For the generation of initial radical, a broad variety of suitable precursors can be employed, such as halides, thio, selenoethers, alcohol, aldehyde, and hydrocarbons. The cyclization steps usually involve the intermolecular additions of a radical to a multiple bond. Most often, carbon-carbon multiple bonds are employed. However, there are also examples known for addition to carbon-oxygen and carbon-nitrogen bonds. If the radical in a resulting intermediate ends up outside of the ring, the attack is termed as exo. If it ends up inside the newly formed ring, the attack is called endo. In many cases, exocyclization is favored over endocyclization. 5-hexanyl radicals are the most synthetically useful intermediate for radical cyclization because cyclization is extremely rapid and exoselective. Although the exoradical is less thermodynamically stable than the entoradical, it is rationalized by beta orbital overlap in the chair-like exo transition. It is transition state. Depending on the method employed, the cyclized radical is converted to the desired product by trapping with the radical scavenger by a fragmentation reaction or by the electron transfer reaction. In general, production of small size ring in radical cyclization is very rare. However, it is possible the cyclized radical can be trapped prior to reopening. This process can be facilitated by fragmentation or by stabilization of cyclized radical. 5 and 6 membered rings are the most common size product by radical cyclization. Polycycles and microcycles can also be formed using radical cyclization reaction. In former cases, rings can be performed and a single ring closed with radical cyclization or multiple rings can be formed in a tandem process. Finally, there are several cyclization processes such as cationic cyclization, anionic Michael type cyclization, and metal catalyzed cyclization. In comparison to cationic cyclization, radical cyclization avoids issues associated with Wagner-Merwin's cyclization, Wagner-Merwin's rearrangement, and does not require strong acidic condition and can be kinetically controlled. Cationic cyclization are usually thermodynamically controlled. Radical cyclization is much faster than analogous anionic cyclization and avoid beta elimination side reaction. Anionic Michael type cyclization is an alternative to radical cyclization to activate olefins, whereas metal catalyzed cyclization reaction usually requires mild basic condition and substituent must be chosen to avoid beta hydro elimination. However, the primary limitation of radical cyclization with respect to these other methods is the potential for radical side reactions. In conclusion, radical reaction must be carried out under inert atmosphere due to radical side reaction. Therefore, concentration must be carefully controlled to optimize reaction condition, yet reaction can be carried out in almost any solvent. That's all. Thank you.